Okay, we're gonna pick up where we left off in the last video. As usual, I'm re-recording this because I lost my chapter 5 part 3. So we're essentially starting with chapter 5 part 3. Okay, chapter 5 part 3. Okay, after defining what an electron pair group is or an electron group is, I'm now moving on to the overall electron geometry. So the last time we talked about this, we mentioned that even though Lewis structure shows the bonds and the lone pairs to be either horizontal or vertical, the real molecules are actually more 3D than they are 2D. They're not flat. And the bonds are not necessarily always horizontal or vertically aligned. They tend to be arranged based on minimizing electron repulsion. Okay. So the Vesper theory is the one that tells us that the electron groups around the central atom will be most stable when they are far apart as possible. So the electron groups rearrange themselves to minimize electron pair repulsion. And so this theory is all about minimizing the repulsion between the electron pairs. Now remember, electron pairs can be bonds. So electron pairs here can be bonds or bonded groups, or they can be lone pairs. Okay. So for the next section, we're going to be looking at what is happening around the central atom. Okay. So let me scroll slowly, not too fast. Right here. Okay. We are able to get different geometries based on the way the electron groups are oriented around the central atom. Okay. So from here, we get 5 basic arrangement. Remember, if Lewis's theory was a perfect representation of how the molecule was, all we'll have is 2D structures. Everything will be flat, and all the bonds will be either vertically aligned or horizontally aligned around the central atom, right? But in reality, what we see right here is the electron groups, once again, they repel each other and then they rest in positions where the amount of electron repulsion is minimized. Okay, so from here we get 5 basic groups or 5 basic arrangements of these electron groups around the central atom. The first one is called linear. In a linear fashion, you essentially have a central atom. So let me call the central atom A. I don't want to define the element, okay? Surrounded by 2 other atoms. So I'm going to call them X because this is actually a way of representing molecules when you have 2 electron groups around a central atom. So you have one central atom, that's this one right here. This is the central atom. And it's surrounded by 2 other atoms. These are the surrounding atoms. If that's what you essentially have a linear configuration. Why linear? Because the 2 electron groups you have right here, they will move and align themselves so they are as far away from each other as possible. Why do we have the linear arrangement? Because in this arrangement, you have the minimum possible electron repulsion. So when these groups are far away from each other, they're repelling each other the least, right? And so 2 groups will produce linear geometry. We have a visual here. This is what it looks like. When you have 2 central atom, 2 other groups, we end up having linear geometry. Okay, so these are 2 examples of linear geometry. Central atom, 2 other groups. And when you have that, the angle when it's measured between the 2 electron groups ends up being 180, like the degrees we have in a line if you're taking geometry, right? A line has 180 degrees. Okay. When we have 3 electron groups around the central atom, this time what we have, oops, I'm still trying to get you used to this new feature. If you're erased and you lift the Apple Pencil from the iPad, the erase feature stops. It's very, yeah, this is different. Okay, hold on a second. Let me go ahead and focus here. It's a little hard. It's been a long day. Okay, trigonal planar. When you have a central atom surrounded by 3 other groups, okay, that's not the best. For me, visually, trigonal planar looks like a Y. You have a central atom and there are 3 other groups right here. So central atom, 3 other groups, looks like a Y. upside down Y or right side up Y. You get the idea, right? Our example here is shown BF3 once again. I don't know why they showed us linear again. Okay. So they're trying to make a point here that if you have two balloons and you tie them at the neck in the middle, the balloons will naturally align themselves so they're far from each other. So they're saying the same way the balloons naturally align themselves this way, so do the bonds. The bonds naturally align themselves to minimize the interaction between the bonds, right? They're kind of introverted, they like their space. When you have three bonds or three electron groups, like having three balloons that will align themselves in this fashion, here we see the electron groups align themselves so they look like a Y, right? We have three electron groups, each of them here being a bond. And with that, we get a bond angle. The angle between the two bonds, adjacent bonds, will be 120, okay? This geometry of this arrangement is called trigonoplanar geometry. And so I showed you guys the table and how to read that table, right? And so I'm going to be building that table just to show you how that plays out. Okay, and so we have covered essentially linear, trigonoplanar, tetrahedral. So by the way, while I'm going through this, I need to mention something. So much comes to me when I'm talking about these things. Linear is 2D. Linear tends to be flat because it's just a line, right? Trigonoplanar, planar means flat. Trigonal means you have 3 points, right, in the triangle, or there are three atoms surrounding the central atom. So this is also 2D. It's flat because it says planar. Planar just means flat. Okay. Tetrahedral is the first geometry that is 3D. This is actually 3D. Okay, so flashback for me. Years ago, I was learning this, right? In our curriculum, the first time I heard of tetrahedral, I was in middle school. And I'm looking on the board, I'm thinking to myself, yeah, I'm not gonna make it out of this class. I'm not great with like vocabulary. I told you guys that in the previous video. And I'm struggling to connect with these shapes. I get linear. Trigonoplanar is somewhat obvious. Tetrahedral, I get the four, but I'm like, I'm not gonna remember this. So I'm trying to make up things in my head that kind of will help me remember this. You know what came to my mind? A chicken's foot, because this is what it looked like. I mean, I could have gone with tripod stand, but this is me in middle school trying to connect with the material, right? So I came up with chicken foot, and I was trying to be funny too. So I'm like chicken foot. So from here on, tetrahedral looks like a chicken foot, right? And this is 3D geometry. It's not flat. It's actually 3D. It looks more like the tetrahedron from geometry once again. And because it's not flat, if it was flat, it will be like this, and the bond angle here will be 90. Because it's not flat, it's 3D. The bond angle is 109.5. I had to remember the bond angle 109.5. Y'all know I come up with a story, right? So this time my story was um back in my days and when I was younger, it was a thing to have a radio station. When you met another young person, besides finding out their names and their hobbies, you ask them, hey, what is the radio station you listen to? So to appear cool, you want to have, a cool radio station that has all the nice jams, nice music and stuff. So I was thinking, I think 104.5 or something was the radio station at that time. And it had to be FM, okay, not the other one. It had to be FM, not AM. And so I was thinking to myself, and my mind is just wondering, man, if I had money, now I'm in middle school, I don't even have a job, but hypothetically, if I had money, I would hire, first of all, I will rent the 109.5 frequency. I know it's not a radio frequency, but remember, I didn't have money either or a job. And I'll hire this guy with a very deep voice because my favorite radio station, there was a guy with a deep voice, but I will be the boss and I'll get to hire this guy with a deep voice. And what will he do on my radio station? Talk about everything chemistry related, all these pun jokes, all these non-funny jokes. He will tell all those jokes, and only people in the in crowd will get the joke. Anyway, I know it's an elaborate long story, but you know what? I didn't forget. I did not forget 109.5 because that was my radio station. So we have chicken foot tetrahedral, bond angle 109.5. Okay. Anyway, moving on. Let me show you what it looks like over here. This is what it looks like. 109.5 right there. See, when you have four groups that are aligned around the central atom, their natural geometry is tetrahedral geometry, aka chicken foot, with a bond angle of 109.5. Okay. Next one we see here is when you have five groups around the central atom. Now, these are just the introduction, right? And this is assuming all groups are bonded groups. When you start looking at bonded groups and lone pair groups, you start having variations from these ideal uh, arrangements, okay? So when you have five groups around your central atom, you have bipyramidal. So I'm like, okay, so this is like two pyramids, right? And you see the structure, it does look like two pyramids, depending on how you look at it. Then we have octahedral, and octahedral has nothing to do with eight surrounding elements. But I'll talk about that later on. Okay, but we're told here based on the maximum number of bonds or electron groups, we're looking at 6 electron groups maximum. We're not going beyond that. Okay, we're told here though there may be more than 6 electron groups. These are very rare. This is still general chemistry, so we're going to keep it general. Okay, so I'm done with the slide. Check. I like checking a slide. This one is done right here. We have done the tetrahedral 109.5. Now let's answer this question. Okay. In determining electron geometry, why do we consider only electron groups on the central atom? Why don't we consider electron groups around the terminal atoms? So remember that the electron groups are kind of coalescing or meeting on that central atom, right? And the electron groups have to be close enough to influence each other so they can repel each other. So when they're around the central atom, this is where they meet. I'm looking at four groups right now. So they have to kind of be close together to influence each other. We are focusing on the shape or the geometry happening around a central atom that we have picked. And because of that, we only consider what is around that central atom. Now, is it possible for us to look for the geometry on a surrounding atom? Yeah, that's possible. But when we do that, we make that the central. Central is just where our focus is. Does that make sense? So don't combine the central and the surrounding, because if you're looking at the surrounding becomes the central. The central is always what we're looking at. It's always the focused atom, if that makes sense. Okay. So we don't look at terminals, because if we're looking at terminal atoms, we're now making them the central atom or the atom of focus. Hopefully this is not confusing. Okay, let me continue. So I feel like I'm saying a lot. There's a lot to be said, y'all. I try to keep it simple. It's hard. Okay, so we're moving on here. So the assumption here is you've already drawn the Lewis structure, right? To figure out the molecular geometry, which is the same thing as the shape, this is the more formal name, the government name, molecular geometry. The street name is the shape, and there is no street, but y'all know what I mean, right? The casual name. Same thing. Okay. Let me make sure I'm recording here because, yeah, the times when I've just been talking for a while and I realize I haven't recorded, it's a mess. So let's go through. What is the geometry of HCN molecules? So it's assuming that we've drawn the Lewis structure, right? So the process is you have a molecule formula or the name, you draw the Lewis structure. Then from there, you find the geometry. So from here, we have two electron groups. How do I know that? These bonds are grouped together. They're stacked together, right? Like pancakes. It's a group. Here's a group. So essentially have the central atom surrounded by two groups, and therefore we have linear. That would be our answer. Okay. So at some point, I am going to go over that big table by myself and draw it out so y'all can see how this plays out. Okay, so back to the types of electron groups. Now we're looking at the trigonal bipyramidal. Okay, so with this one here, it's a little tricky. So I'm going to draw it out here on the side, then show you the picture. With this one here, apparently the groups have different names. If the groups are, say A is a central atom. If you have a group above the central atom and below the central atom, those groups have a different name and they're called axial. Okay, the positions above and below the central atoms are called axial. This only exists in the trigonal bipyramidal because stuff is complex here. Okay, and then when the groups are coming out from the waistline, they're called equatorial. And the way I thought about this is kind of like if if you as a person was the center, the area of focus, and then you had things coming out of your waistline towards the outside, that will be equatorial because it's in the equator position, right? Equatorial. And then if something was coming out from your head facing the ceiling and from your toes facing the ground, those would be axial. So up and down is axial, and then equatorial will be around your waistline. Okay. And for that reason, the bond angle between up and the between axial and equatorial should be 90 degrees, right? Hopefully that makes sense. Anyway, let's see it happening here. So we have equatorial right here, and these are axial, and you see the bond angle between them is 90 degrees. But between two equatorials, if you have an aerial view from top to bottom, this is an axial position. What you will see is three groups that look like a Y. So guess what? Once again, the bond angle here is 120 degrees, like trigonoplanar. So essentially, to get trigonobipyramidal is like taking trigonoplanar and then putting a bond above and below. It doesn't look right, does it? Anyway, this is this. Let's go with their picture. It makes more sense. Okay. And then finally, the octahedral electron geometry. With this one here, we have a central atom surrounded by 6 atoms, right? So why is it called octahedral, you ask? It is called octahedral because the geometric figure has got 8 sides. You can actually place 8 triangles on the corners, right? Like that, 8 triangles. It's hard to really draw it, but yeah, it has 8 sides. Now, in this case here, we don't distinguish between the top and bottom atoms and then the side atoms. Why don't we distinguish them? Because they're pretty much alike. They have the same bond angle, right? So the bond angle here is 90, top and side. Side by side is 90. Yeah, so the bond angles here is just 90 degrees. I would say of all the groups that's complicated, the trigonobipyramidal is complicated. Why? Because there are 2 different types of surrounding groups and you have 2 different bonds, right? Top to side is 90 degrees, side and side is 120 degrees. So you have to remember that. Okay, moving on. I'm not going to work this out from scratch. I'm going to make assumptions. You remember Lewis structure. And the Lewis structure for NO3, real quick, I won't really draw the resonance structures here, but real quick, nitrogen is, we have 1 in the formula. It's in group 5, right? Oxygen, we have 3. It is in group 6, right? This is where I need a live audience, y'all. I need a live audience. So we have 1 times 5 is 5. 3 times 6 is 18, right? Then you have the negative here, add 1 plus 1, and we end up with 24, right? 23, 24. Okay, central atom is nitrogen, surrounded by 3 oxygens. We have oxygen, we got oxygen, we got oxygen, right? Then you use electrons from here to form single bonds. 1, 2, 3. 3 is minus 6 electrons because we use 2 electrons to form a bond, right? We're left with 18. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So minus 18. 6 times 3 is 18. We are out of electrons. Okay, we check and see that all the oxygens do have octet, right? The nitrogen doesn't. It only has 6 electrons. To help the nitrogen get to 8 electrons, let's use the electrons from here. Oh no, I erased everything. Okay, double bond. Okay, once again, since we have to use a negative charge to make this work, I have to put the brackets around it and put a negative there. Okay, now the question here is determine the molecular geometry. Remember, molecular geometry, once again, is the shape. And so for this, we need what? 3 electron groups? 1, 2, 3 electron groups, and all of them are bonds. So 3 electron groups look like a Y, right? So that's trigonoplanar. This will be trigonoplanar. Okay. And don't forget, we do have resonance structures. And each of these resonance structures will essentially be trigonoplanar. And remember, we're told the hybrid structure is an intermediate between these 3 and has three equivalent bonds. Okay. So it's common to get a question on the exam asking you what is the bond value between one nitrogen and then one oxygen. Of course, you will not say, well, we have one single bond and sorry, one double bond and then two single bonds. No, you will say we have all three bonds are equivalent, right? And you have a solid bond and then you have a dotted bond. So the bond order here will, of course, be 1/1/3, right? Go ahead and review resonance structures, but yeah, that would be essentially the hybrid structure right here. Okay, moving on. So yes, since there are three bonds that are equivalent because of resonance structures, they exert the same repulsion on the other two, and therefore you have trigonal planar, trigonal planar geometry with a bond angle of 120 degrees, right? Okay, we're not doing the four practice problem, we're moving on. Okay, so I want to mention this part here before we go into the big table because it's important for us to notice that what we have dealt with so far, all the structures we've dealt with so far do not include lone pairs. Okay. So apparently there is something called the effect of the lone pair on the molecular structure. Lone pairs have an effect. Okay. I'm trying to think of something that I can relate this to in life. It's kind of complicated, right? Sometimes. But let me get to it. Bottom line is the effect has to do with the amount of space taken by these pairs. So remember, what we're doing here has to do with electron groups. And these electron groups, the ingredients of the electron groups come from pairs of electrons. Okay. I'm trying to say what I've said differently so that y'all, hopefully it makes more sense as I'm saying this differently. The ingredient that makes electron groups, it's essentially pairs of electrons. How does a pair of electrons get presented to us? Well, it comes in two forms, either as bonded groups or lone pair groups. Okay. So the bonded groups can be single, double, triple. These are all bonded groups, right? And we know bonds are formed when electron pairs are being shared. So these are shared electrons. Share. Yeah. On the right, we have lone pair electrons. These are not shared, they belong only to one element. So you can say, oxygen can be in a bond, but it can have electrons belonging to itself. And of course, these are not shared. They're the opposite of shared. Okay? They belong to the element alone, ergo, lone pairs. Okay. So apparently, we're being told here that lone pair electrons take up more space. Okay? How did they articulate that? You see all the space they take right here? They're somewhere in here. They take up a lot of space. They spread out. They're not being held between two elements. So they kind of spread out and take up a lot of space. Okay. But remember, the whole Vesper model was saying electron groups are trying to stay far from each other. Well, how do you stay far from something that's taking up a lot of space when you want your space? You kind of move away more, right? So the issue that happens here is when you have two lone pairs side by side, because each pair is taking up space, they kind of push on each other more because it's a complicated relationship. They're taking up more space, but they want space. I'm like, take up less space then, you know? But they're taking up more space, but they want space. So they push on each other a lot because they spread out, but in the process, they repel each other even more. Okay. On the other hand, bonded electrons are more restricted, so they don't really spread out as much, right? Bonded electrons. So here you have, let's say, like an oxygen bonding with another oxygen, and this is the bond between them. I don't know why I chose that. Okay, maybe a hydrogen. It doesn't really matter what the element is. The point here, oh, come on. Yeah. The point I'm trying to make here is it doesn't matter what the element is. We're just showing bonded versus non-bonded. Let's say this is two hydrogens, right, forming a bond. So it looks more like this. The bonded electrons are restricted on how far out they can go because they are being shared by the two elements. The two elements sharing the bonded electrons are kind of locking them in place because their whole relationship is built upon these two electrons being shared, right? So they're kind of, this is the space that they're able to kind of be in. So this is almost like the orbital of the shared electron. Think of it that way. They can be somewhere in that space, but they can't be outside that space. On the other hand, look at how much space the lone pair electrons have. They have more room. Okay. They have more space to spread out. Anyway, the bonding electrons are shared between two atoms. So some of the negative charge is removed from the central atom. Okay. In this case here, we're told relative sizes of repulsive force interactions are as follows. Remember, two lone pairs spread out, right? And then they repel each other a lot. So for that reason, the lone pair repulsion is the biggest. If you have two lone pairs side by side, the bond between them, or I guess the space between them, will be really big. Okay. Where do we see two lone pairs next side by side in the molecule? Where, let's say, when you have water, we have two lone pairs side by side. Because the lone pairs occupy a lot of space, they push on each other a lot. And this pushing affects how close they are to the bonded groups. And therefore, they push more on the bonded groups. They spread out more, forcing the bonded groups close to each other. So even though this molecule here should have 4 electron groups and the bond angle should be 109.5 degrees, it ends up being approximately 104.5. Why less? Because the bonds are being forced together. It reminds me of this machine at the gym where there is, I want to call it the abductor or adductor. I don't know. Is that machine where you sit there and you put your legs here and then the machine pushes your legs together, right? Like that. And you try to push against the machine and then you lose. If you lose, you're using too much weight, but you get what I'm saying, right? So these two lone pairs push on the legs, on the bonds, sorry, and force them close together. Okay. Lone pair versus bonding pair is the effect is not as much because the bonding pair doesn't have the space. It doesn't occupy as much space as the lone pair. And then bonding pair versus bonding pair, the effect is so much less, right? So two bonding pairs, you get 109.5. The most separation. Bonding pair versus lone pair. Let me try to write the bond angles here. Okay. Lone pair to lone pair, we get 104.5 between the bonds. Not between the lone pairs, but between the bonds. Lone pair to bonding, we have 107. And then bonding to bonding, we have 109.5. Okay. So this is shown, oh, they show something else here. This is shown right here. Okay. Once again, one lone pair pushes down on the bonds. Here, two lone pairs push down the bonds. So come back to that right here. Where all the bonds are bonded groups and no lone pairs, we have the perfect bond angle of 109.5. When we have one lone pair here, then the remaining bonds are a lot closer, so we have 107. When we have two lone pairs here, they're invisible. Then the remaining bonds are even closer than this geometry here. We have 104.5. Okay. Now I want to say this. Once again, this is the effect of lone pairs on molecular geometry. So bottom line, lone pairs cause remaining bonds to move closer, decreasing bond angle. So whenever you see that a molecule has less than the ideal bond angle, you know what's present, right? A lone pair. Because its effect causes this. If you have less than ideal bond angle, it's because somewhere in that structure around the central atom, there is a lone pair. Okay. Okay, where was I? Okay, I think I mentioned electron pair geometry before, right? I feel like I've gotten far enough. Let me go ahead and mention this part here, and then I'm going to go and start the structure. I feel like I'm just, yeah. Actually, you know what? Let me go ahead. I've gone far enough, and then I'll come back to right here. Okay. So now I kind of need to create a table. I'm trying to think to myself, how am I going to survive this? Okay. This one here has to be good. And this one here. Okay. Okay. So electron groups. Okay. We're just going to be doing a number right here. This should work out. And then bonded groups. I think I'm feeling a little bit more confident. Lone pairs. Okay. Electron pair geometry. Okay. Molecular geometry. Let's see. Metry. Ooh, okay. I guess this is gonna work. I'm gonna start with the formula CS2. In CS2, I'm gonna draw the Lewis structure, follow the rules here, and then of course we'll go from there. So Lewis structure, our central atom is C, surrounded by two S's, right? Carbon is in, we have one in the formula, it's in group 4, so it brings in 4 electrons. Sulfur, we have 2 in the formula, it's in group 6, it brings in 12 electrons. We're working with 16 electrons, right? I'm gonna write them here and erase them later. Okay, so we're gonna form a single bond that uses up 4 electrons. We're left with 12 electrons. Then we put 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I use the 2. This is gonna be tricky. I need this tiny, tiny, tiny piece here. Can I get it smaller than that? Oh, great. Use those electrons right there. Okay. And then form a double bond here, a double bond here, and we're done with the Lewis structure. So I'm going to erase this part. Oops. Yeah, this was great, then it wasn't. Okay. Better. It's tricky to switch back and forth, but here. Okay, how many electron groups do we have? Electron groups, I'm going to use the highlighter. I want to use yellow. So this is one electron group right here. Here's another electron group right here. We have 2 electron groups. 2 electron groups. How many of them are bonded? Both are bonded. We are only focusing on the electron groups around the central atom, not the surrounding. Remember, the central atom is the atom of focus. This is what we're focusing on. What is touching it? It's carbon. Everything's about carbon, not sulfur. So we have 2 bonded groups, right? 0 lone pairs on the central atom. Do we have lone pairs in the sulfur? Yeah, but that's not what we're focusing on right now. We are focusing on what's in the middle. Okay. When you have 2 around the central atom, the electron pair geometry is called linear. Okay. The molecular geometry is also called linear. So I need to pause here for a second. The electron pair geometry, this one here is based on all groups present. So the name of the geometry is the name considering all the groups present around the central atom, right? Molecular geometry only focuses on bonded groups. Bonded groups only. I know I'm running out of room because there's a lot to say. Okay. So as long as we don't have lone pairs to make a difference in the molecular geometry name, molecular geometry will have the exact same name as trying to move this over. Oh, okay, great. It had the same name as the electron pair geometry. Okay. Our bond angle we saw earlier was going to be 180. Perfect bond angle. What is AXE? I casually call it the X effect. Remember earlier I was saying you had a central atom, A, some random atom, A, and then the surrounding atom was X. Okay. So A stands for the central atom. That's a way of kind of communicating about the formula, but not being non-committal with the elements. And chemists do that a lot because they're like, I don't want to say something because if I say something, I have to think about the actual bond. I have to think about it a lot. So you're kind of low-key being lazy, but not really. Okay. Keeping it general without really being very non-committal. Central atom, then you have surrounding atoms. So the central atom is A. So in all your axes, you're gonna have one A because we're always focusing on one central atom at a time. And in the surrounding atom, well, it depends on how many you have in the formula. In our case, in CS2, we have two surrounding atoms, and we had no lone pair. If we had a lone pair here, this would be E, and each surrounding atom will be X, right? So when we consolidate this one here based on our structure, oopsie, nope, that's not it. Okay, I messed up this one here. So based on the structure here, we have A for carbon, and then the two sulfurs will be like this. Then you consolidate. So we have one A surrounded by two X's, right? Okay, that's the first one. We're moving on. First one. Okay. Next one is going to be BH3. Oh, by the way, for the two electron groups, this is all we have. I'm going to kind of highlight this here so you can see. Oops. It needs a highlighter. For the two electron group, this is all we have. Okay. For the three electron groups, I'm going to go the pink color and let's see how that plays out. We got B. Oops, wrong. I am doing the most. What's the marker here? We got BH3. Okay. So in BH3, I got B, I got H, I got H, I got H. Once again, Lewis structure. Boron, we have one in the formula. It's in group 3. 3 electrons. Hydrogen, we have 3 in the formula. It's in group 1. Each of them is in group 1. 3 electrons. We're working with 6 electrons, right? We use our 6 electrons to form a bond, a bond, a bond. So we are left with no more electrons. Okay. Oh, can we double bond to make boron get to 8? No, we can't because none of the hydrogens even have any lone pairs. So that is it for boron. Resist the urge to double bond boron. Okay, let me tell you all something. I looked at my grad school work at some point, and you all know I actually had double bonds on boron. I don't know if you can hear me whispering, but on one of my work, and my teacher marked it wrong. And I look at younger me, I'm like, younger me, what were you doing? Not focusing. Not focusing. Okay, how many groups do we have around the central atom? We got 1, 2, 3. Remember, elements before carbon do not form octet if they're central atoms. Carbon is the first one that forms octet. Okay, we're keeping it simple. Okay, over here, next one. How many groups do we see here? We see 3. There's 3 bonds attached to boron. There's 3 groups. All 3 are bonded groups. Okay, so I want to highlight this so we can see. Wait, highlight this. So this is the first of the 3 groups. Okay, back to this. All 3 are bonded groups, no lone pairs. So the name of the shape, well, the electron pair geometry will be trigonal or triangular, planar. It's flat. 3 groups are on the central atom. Okay, there is no lone pair, so the molecular geometry also is trigonal planar. Okay, bond angle, since we have that the Y shape, this will be 120 degrees. Okay. While we're talking about question types, you can be given a question where the structure is drawn following the Lewis format. In the Lewis format, it looks like this. And you're asked, what's the bond angle between BH and then BH, like the bond angle between here? Please resist the urge to give a bond angle based on how it looks. You want to follow this process and go with this bond angle here. Do not say this is 90, even though I drew the bonds like they were not 90. You know they're not 90, right? Vespa tells you what the bonds do to each other. They repel each other. Okay, right here I have what? I have 1 central atom and I have 3 surrounding atoms, AX3. Okay. Okay. Next one is going to be, I have them kind of listed here, O3. So O3, central atom O, surrounding atoms O. Oh, yeah, just pick one of the O's to be the central atom. I need to go back. And then erase this one here. I was trying. Okay. Okay. So we have oxygen 3 times. Each brings in 6 electrons. In group 6, we're working with 18 electrons. Single bond, minus 4 electrons. We've drawn 2 single bonds. We're left with what? 14 electrons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. minus 12 electrons, we're left with 2. So 1, 2. Ooh, what was I doing? Sliding 1, 2. Okay. To help the oxygen in the center get to octet, you're going to remove one of these electrons over here, or pair. Ooh, that was hard to draw. And then put it here. And that's how we get to octet. Okay? It's a balancing act, y'all. Okay. So we're here. Now that we're here, what do? We're going to go ahead. Let me draw this here like that. Okay. How many electron groups do we have here? Okay. This is a group. Remember, if they're together, if they're grouped together, they're a group. The emphasis is together. Oh no, the emphasis is grouped. I wish they said grouped together, but yeah. If they're together, they're grouped together. So we have 3 groups, right? But in this case here, not all 3 groups are bonded groups. By the way, this is a variation from the one where all 3 were groups. We're now seeing a situation where we have 3 electron groups, but not all 3 are groups, right? Sorry, not all 3 are bonded, right? 2 are bonded groups. 1 is a lone pair. The lone pair is right here. Oh, well, electron pair geometry is based on the electron groups present. So this would be, it's still 3, so it's going to be trigonal planar. Trigonal planar. Molecular geometry, on the other hand, that is based only on the bonded groups. So remember, we're starting off with a shape that looks like a Y, right? And we're taking away the neck of Y. What does it look like? A V, right? In the world of the chemists, they're like, V is not straight? No, it's bent. It's like not straight. So they call this bent. I try to make a backstory to justify the names, right? Like somebody was very disappointed that the remaining bonded groups did not become a straight line, and so they call it bent. Like it somehow missed the mark. The bond angle here, since we have a lone pair, it would not be the perfect 120. It's going to be less than 120 degrees. Okay. Oh, the axe effect, right? Since we have a central atom, 2 surrounding atoms, and 1 lone pair, you're going to write 1A, 1 central atom. Now we have 2 surrounding atoms. So 1 less X and then 1E, because the E is replacing 1X. So it's going to be AX2E. Okay. Now we're done with the 2 groups, right? We're done with the 3 groups. We're done with this and this. So now we're moving on to the 4 groups. Okay. Can I erase this without creating a lot of situations here? Let me make this small. Okay. So with 4 groups, we're going to be dealing with CH4, NH3, H2O. Okay. So once again, we got carbon in the middle, surrounded by 4 H's. Really Lewis structure. Right? Carbon is one in group 4, we have 4. Hydrogen is 4 in group 1, we have 4. We're working with 8 electrons. You draw a single bond here, here, here. Uses up all 8 electrons and we are out. Okay? Trying to conserve space and speed up time. Not speed up time, but speed up my process. Okay, so how many, let me use a different color now. How many groups do we have here? 1, 2, 3, 4. We have 4 groups, and all 4 groups are bonded groups. We have 0 lone pair groups. There's no lone pair anywhere in that molecule, not even the central atom. Electron pair geometry with 4 groups, we have tetrahedral. Right? Molecular geometry, same thing, tetrahedral. Because, let me write this diagonally, I'm running out of room. Tetrahedral. Okay. Bond angle 109.5. AXE, we have 1 central atom, 4 surrounding atoms, and no lone pair. So AX4. Okay. Now, we know the trend, right? This is 4 surrounding groups, and all of them are bonded groups. So the theme will be, you know what it is, right? And the next one here, we're going to have 4 surrounding groups. Let's see how that plays out. Nitrogen surrounded by 3 hydrogens, right? Nitrogen, we have 1 in group 5. This is 5. Hydrogen, we have 3 in group 1. This is 3. 8 electrons. We put 1, 2, 3 here. Minus 6 electrons. We're left with 2. 2 going in the center. We are out. Okay. Let's go ahead and use this right here. Okay. So how many groups do we have here? This is a group. This is a group and a group and a group. So we got 4 groups. But this time, not all 4 groups are bonded groups. Only 3 of them are bonded groups, and then 1 is a lone pair. So you're seeing the same thing we saw before. You keep replacing a bonded group with a lone pair. As the bonded group number goes up, down, the lone pair number goes up, right? Electron pair geometry based on all 4 groups, it's going to be the same. Tetrahedral. But now let's go back to tetrahedral. Remember that was a chicken foot? This is bothering me here. I need to stop obsessing. That was a chicken foot, right? So this time you're kind of breaking the foot. No, these are the toes right here of the chicken. That's the claw. Okay? You're breaking the foot of the chicken. Oh, I didn't realize there was stuff over there. You're breaking the foot. Or should I say the leg right there? So now your chicken looks like that. These are just the fingers of the toes of the chicken, right? Remember that forms the shape pyramidal. So this becomes trigonal pyramidal. If you're going with a tripod stand analogy, it would be like taking the stand of the tripod stand and breaking that stand. So you just have, the legs of the stand there, And so the bond angle here is not a perfect 109.5 because you have lone pairs. It's going to be less than 109.5, or you can say 107. Okay. The AX or the X effect will be you have 1 central atom A, 3 surrounding atoms X, and then 1 lone pair E, right? 3 surroundings, 1 lone pair. Okay, let's go with water. With water, you have a central atom O surrounded by 2 surrounding atoms. Okay, and we have oxygen in the middle. 1 times 6 equals 6. We have hydrogen. 2 times 1 equal 2. This is 8. Okay, we have a lone pair. Lone pair, bonded groups. Minus 2 electrons each time, so minus 4. We're left with 4 electrons here. 1, 2, 3, 4. And then we're out of electrons, right? I'm running out of space. And for a moment there, I kind of zoned out a little bit. Okay, so let's go ahead and count the number of electron groups here. This is a group, a group, a group, a group. So we are surrounded by 4 electron groups. Let me highlight that so we can see the theme of 4. So in the 4 electron groups, only 2 are bonded groups, 2 are lone pair groups, right? So while this is going down by, the bonded groups are going down by 1, the lone pair groups are increasing by 1. Once again, electron pair geometry to tetrahedral. And then the molecular geometry. Let's go back to our structure here, which I need to erase and draw it a little bit higher. Let's go ahead and take, we had our chicken foot, right? I'll draw it here. We had our chicken foot. We broke off the leg. Listen, no violence is done on a real animal. This is a hypothetical chicken foot, okay? And then we're breaking 1 toe. It sounds like torture. What shape remains? Think like a chemist. Not linear. So this is going to be bent again. Okay. I've been asked before, oh, do we have 2 bends? Yes, 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 we have 2 bends. And I asked, how can you tell one bent apart from the other bent? Because if you're just dealing with something bent, you walk into a situation and you see a molecule that's bent. How can you tell you're looking at the tetrahedral bent or trigonoplanar bent? And I got the answer I wanted from the bond angle. Measure the bond angle between the 2 remaining bonds. If you get 120, it's trigonoplanar bent. Oh, sorry, it won't be 120. If you get like 119 less than 120, it's going to be trigonal bent. If you get like 104-ish, it's going to be tetrahedral bent, right? It's all about the bond angle. It's all about the bond angle. 104.5 for this bond angle here for the remaining bonds, right? Now to the molecular type or the AXE effect. You got A for the central atom. Central atom is oxygen. Surrounding atoms are hydrogen. Two X's, X2. And we have two lone pairs right here. E2. Okay? Just like you saw before, number of A remains constant. We have one central atom. The surrounding atoms reduce each time by one, and then the lone pair builds up. For every surrounding atom lost, we have a lone pair. Okay, we're moving on to our next group. Okay. And once I finish up this part here, this is pretty much most of the chapter being done, right? This time I am moving on to the next shape, PCl5, SF4, BRF3, XEF2. Okay. So P in the middle, Cl, Cl, C, that's axial, equatorial right there. Okay. So P1 times group 5 is a cousin of nitrogen. Cl 5 times 7, 35. And here we got 40, right? Okay, 40 electrons. 1, 2, 3, 4, 5. That's minus 10. We got 30 electrons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Oh, I need to pick a color for this. Let me pick a highlight color because I was kind of going in order, right? Orange is next. So this time we're going to be doing 1, 2, 3, 4, 5 groups. So we're working with 5 groups of 5. And the theme for 5 groups is orange. Orange. Okay, bonded groups. 5. Lone pairs. There is no lone pair attached to P, right? The lone pairs are attached to Cl. So let's say nope, no lone pairs attached to P because P is our central atom, our atom of focus. Legend pair geometry, trigonal bipyramidal. Same thing with molecular geometry, trigonal bipyramidal. It's hard to write this. I don't really have a lot of room. Bond angle. We have 2 bond angles, right? I showed you guys before. The top and the side was 90. So we have 90 degrees. And the side and the side was 120. So we have 2 bond angles here. AXE. A, of course, X, 5. There's no E, no lone pair in the central atom. Okay? So I want to show you something, right? Without even doing the stuff on the left, I can show you how the AXE plays out. The next one will be A. The A doesn't change. The X decreases by 1. So we have AX4 and then E1, right? Next, AX3, E2. Next, AX2, E3, right? So you see how that plays out? Anyway, let's go back here now. We're going to have S. Oh, for the name of the different shapes, you have to remove the right molecule, right? The right surrounding element of the molecule. But okay, so the first one you have to remove has to be one on the equatorial region. So we're gonna go with S, F, F. So the axials remain intact. Then you have an F, and I remove the one to the left. The one that was supposed to be here, gone. Okay. So when it comes to electrons here, let's see. Sulfur is 1 in group 6, we got 6. Fluorine is 4 in group 7, we got 28. We add this up and you get what? 30, 34. Okay. Okay, so 34. We got 1, 2, 3, 4 minus 4 times 7 is 28 plus 6 is 34 minus 8, 26. Okay. So I got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So what you're experiencing right now is me fading out because I'm just kind of it's a little bit too mundane, so I'm kind of fading out a little bit. And it's been a long day, honestly. It's been a long day, so I'm quickly fading. Okay. So I have to just double check my math so I don't really continue and mess up. Yeah, it happened. It happens. Okay, we got this. I'm trying to encourage myself, keep myself pumped up. Okay, so how many electron groups do I have? Slowly loading back up. 1, 2, 3, 4, 5. We got 5, right? How many of them are bonded groups? 4. There's one lone pair that's on S, right? Okay. Electron pair geometry, trigonal, bipyramidal. Okay. Now, oh yeah, I gotta tell you something. So in class, right? I'm thinking I try to make up these backstories. They're not real. They're just me speculating a lot, hypothesizing, not based on any true empirical evidence. Just me trying to be nosy, right? And make this a little bit interesting. I feel like this one here was named on Monday, right? Why am I speculating was named on Monday? Is that part of the lesson? No. Look at how formal the name is, trigonal bipyramidal. The electron pair geometry, I think, really honestly was assigned on Monday. And then this one here, the name of this molecule, okay, they're like, wait, let's name this molecule. Look at that. There's a lone pair over here, and there's this over here, okay? This is my speculation. And they were like, oh, hey, Bob, you want to go ahead and name this molecule? This is a Friday. And Bob was like, well, when I name it, can we leave? Sure. So they kind of, sharing a little bit of drinks here. And Bob was like, you know what? I took my daughter Susie to the park this weekend or last week or during the week or whatever. Really? Yeah. And I saw some kids playing a seesaw. And I feel like this molecule over here reminds me of that seesaw. And people are like, yeah, heck yeah, we can see that. So you have a kid over here, right? And there's a kid over here. And they're going up and down. Yeah, this is like a seesaw. So they call this a seesaw. This this had to have been named on Friday. I don't see how they could name this name on Monday because the boss is there on Monday, right? The bond angle here is going to be less than 90, less than 120. Okay, we already have the AXE. Next one, BRF3. In BRF3, once again, we got bromine in the middle, we got F on top, F on the bottom, and then one of these F's gone, right? So we only have one left. Okay, BR is 1, it's in group 7. F, we have 3 in group 7. We got 7 here, we got 21 here, we got 28. So we got 1, 2, 3, that's minus 6. We're left with 22. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We got minus 18. So 22 minus 18, we're left with what? 4? 1, 2, 3, 4. Okay. So let me go ahead and erase this. Oh, come on. Yeah, I got it. Okay, there. So let's go ahead and highlight our groups. I have kind of dropped the ball a little bit. Okay, 1, 2, 3, 4, 5. We got 5 groups, right? Let me kind of highlight it here. Highlight. These are all groups of 5, right? This is the orange group. So we got 5. Before I draw this, you know it's gonna be 5, right? That's the theme over here. Groups of 5. Okay, well, how many in the BRF3 are bonded groups? You can see there's just 3. How many are lone pairs? We got 2 lone pairs. So electron pair geometry is based on all groups present. So it's gonna be trigonal. Same name. Bipyramidal. Okay. Now what do we call this? Okay. I think I'm speculating. This was either named on another Friday, like the following week, or Thursday. It's definitely not named on Monday. You wanna know why? Because once again, they call somebody. Since I'm making up this story, I'm gonna make it female this time. Tracy. Tracy, can you name this molecule? She's like, I like the letter T because it's like my name and everything. I'm just kidding, guys. But yeah, so they call this T shaped. When I was in school, I was like, for real? Yep. less than 90 degrees. You don't have 120 here because you only have one equatorial bond. To have 120, you need to have two equatorial bonds or more. Okay, we only have one equatorial, so there's nothing for us to compare it with to get the 120. So all we have left is axial equatorial. So the bond angle here is 90. Okay, finally, XEF2. My handwriting is horrible here. We have XE and then F on either side. Okay, let me write this better so I can have more room. Okay, this is 2 right here. XE, F, F. Okay, so XE, we have 1 is in group 8. We have F2 is in group 7. So we got 14 here. Here we got 8. Total is 22, right? Single bond minus 4 is equal to 18. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Minus 12 equals 6. 1, 2, 3, 4, 5, 6. Minus 6 equals 0. Okay? We can go ahead and erase all of this. Oops. Erase all of this. Ooh, yeah. Yeah, I got some energy back. I drank some water, so it's doing a little better. Let's see. What do we have here? So we know we already have 5 groups, right? Let me highlight the groups. This is 1, 2, 3. Those are my lone pairs. 4, 5, my bonded groups. Okay, so we got 3. Oh, no, not 3. This time it's 2 bonded groups, 3 lone pairs. Okay, because the bonded groups drop by 1. The lone pairs increase by 1. Okay, trigonal bipyramidal for the electron pair geometry for all the groups present regardless of what they are. And then for the shape, I feel like this is just me making up a story again. Disclaimer. The boss got the reports, and because they had the people in the meeting, the committee had agreed on this name, the boss can't override or overturn these names, right? They asked, I motioned to call this molecule a seesaw. Do I hear aye? Somebody confirmed that motion. Then it was passed. I motioned to call this molecule here T-shape. Somebody second the motion. Somebody second the motion. Here, I feel like the boss came in and said, y'all, I need y'all to get serious again. Start giving these names, these molecules, formal names. So in this case, this was named on Monday. I'm just hypothesizing. It was called linear. So we're back to being formal, right? Because the actual bonds that remain are in a straight line. So the bond angle here is a perfect 180. I know, I don't know where. But I was like, wait, how did we didn't even start with 180 and we're ending with 180. Yeah. So actually, you know what? If you're wondering how I got it this way, I could actually draw this vertical so it makes more sense because I was on a seam and then kind of digress. In this one here, we could say XE is in the middle. Then one F is on top, the F is in the bottom. The bond is like that. You have the lone pair, you have the lone pairs, then you have the 6 dots like that. So you have these groups right here. This is a group, this is a group, this is a group, this is a group, this is a group. But nonetheless, it's still linear, right? It's still linear. Yep, and that's it for the group of 5. Now we have to persevere to the group of 6. Okay. Once again, you can go back and erase and erase. Sorry, you can go back and forward this, and I'm trying to persevere through this, and then I'll take a break. I'll probably record tomorrow because I have to go to court early in the morning. Oh yeah, I'm gonna record tomorrow. Let me finish the group of 6 so I can actually finish my thoughts, and then I'll take a break, and then have chapter 5 part 4 tomorrow. So I have SF6, I have BRF5, I have XEF4. Let me do the Lewis structures real quick. I'm going to skip the whole process. We're going to up, down, 1, 2, 3, 4. So it'll be F, 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 F. So we're starting with S being 1 times 6. This is 6. F being 6 times 7. This is, what is it? 42. Hold on a second. 6 times 7. And verify that. 6 times 7 is 42. So we have 48. And then we subtract 1, 2, 3, 4, 5, 6. We subtract 12 and we're left with 30. So it's 36. Okay, that's what I was trying to make sure. 36. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. So we got the structure there. Let me go ahead and erase this. Make this go faster. Okay. With B, R, this time we have F, 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 F. So BR, from BR we get 7 times 1 times 7, right? It's gonna be 7. From F we have 5 times 7. It's gonna be 35. So we have what, 42? 1, 2, 3, 4, 5 minus 10 is 32. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's minus 30. We're left with 2, 1, 2. Okay? I'm doing good. I got one more. I'm trying to do it this way because I am really fatigued right now mentally. I'm trying to push through. Okay, last one. We got XE in the middle. We got F. We got F. We got F. We got F. So I remove the bottom one here. That's where my lone pair is. Now I remove the top and the bottom, right? So XE is 1 times 8. This is going to be 8. F is going to be 4 times 7. This is going to be 28, right? So 36, correct? 1, 2, 3, 4 minus 8. Wait, 36 minus 8, 28. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 times 4 is 24. We're left with 2. Wait, 28. Oh, we're left with 4. So 1, 2, 3, 4. Whew, I made it. Okay. That's the most fatiguing part. For me, it is at least. Okay, so let's go through. We know this is a group of 6. I've already told you it's a group of 6. Let's see how this is. All of these are 6. Let me find a new color for this one here. Gray. Okay, so this is going to be gray. The gray seam, gray seam. These are all going to be 6. How? 1, 2, 3, 4, 5, 6. So this is 6 because all 6 are bonded groups, no lone pairs. Okay, so we're going to focus on counting the groups right here. Highlight. 1, 2, 3, 4, 5, 6. Once again, 6. And we have 5. Oops. We have 5 bonded groups and 1 lone pair. And then here you can see 1, 2, 3, 4, 5, 6. We have 6 total, but then out of them, 4 are bonded groups, 2 lone pairs. Okay. Okay. Selection pair geometry here is octahedral. Since they're from the same 6 electron groups, it will still be octahedral here. And this would be octahedral. Okay, so how's the shape different here? There's no difference in the molecular geometry because we have no lone pair, so it's octahedral. Okay, bond angle just a perfect 90. AXE, 1 central atom surrounded by 6 groups, so it's going to be AX6. Here it's going to be AX5E, AX4E2, right? And that's consistent with the picture that we have here. Okay, on this one here, if you look at it, it looks like a pyramid, right? Looks like we have a pyramid here with a square base, right? So this is called square pyramid. So you don't confuse it with the triangular pyramid or trigonal pyramidal. This is square pyramid or square pyramidal. Okay. Bond angle is going to be less than 90 degrees. Okay. I'm just trying to make it to the end because I'm kind of tired. Okay, here, let's see. Our last line. Since the lone pairs are actually on the top and the bottom, kind of like the axial, but there's no axial here. But if there were an axial, the lone pairs are in the axial position. That makes the remaining bonds actually planar, but they're also square, right? So this is actually called square planar. And the bond angle here of the remaining bonds is going to be perfectly 90 degrees because if you notice, whatever effect we're having on top is going to be canceled out by the effect on the bottom. Okay? And so finally I got done with this part. Oh my goodness, I feel so much better. Let me go ahead and end this video while I still can, and I'll see you guys in the next video.